Hi. My research interest is motivated by one single question. How can we better reason about the correctness of real-world security-related infrastructure? Now, this problem is challenging, and to demonstrate why it's a difficult question, I want to consider an example where we implement a server that stores people's passwords. Here, we're storing people's passwords using a mutable map, and we expose two functions. You can set someone's password, and when you check someone's password, we'll just read from the mutable map and check whether the value stored in the map matches the password we provided. Now, if you ask any security expert, she will tell you, this is not secure. You don't want to do that, because if the database gets leaked, everyone's passwords also gets leaked immediately. And one way of preventing that is to do something called hashing, where instead of storing people's password, we apply a deterministic but hard to invert hash function on the password, and we store that hash into the map. And so when we check the password, instead of checking whether the password matches what we stored, we compare to see whether the hash is the same as the one stored in the map. Now, this solves the problem where, immediately it takes a while for us to crack people's password, but this is still not perfect because, in general, people do use the same password. And if we're able to crack just one person's password, there's quite a likely probability that someone else will use the same password and we crack everyone who has the same password because the same value will be stored in the map. One solution to solve this is to use something called salting in addition to the hash. Whenever we want to set someone's password, we randomly generate a number from 0 to big N, which we call a salt. And what we store in the mutable map is that we store both the salt and the concatenation of the salt and the password applied to the hash. In this case, when two people are storing the same password, there's a high probability that they will be generating different salt, and they will be hence storing different values into the mutable map. And that allows us, and so from the attacker, it's not very clear to see which people are using the same password. Now, just for this example, we can immediately see the use of randomness. And there's actually randomness in two places. We actually need to use randomness to generate the salt, but also, even though the hash function is deterministic, in order to prove security properties, it is often useful to model it as if it's a random oracle. And this brings us to the first challenge of verifying real-world security-related programs. And that is, when you have randomness, the properties we want to verify also becomes more complicated. In addition to the traditional properties we might want to verify, like checking password with the right password returns true, there are certain properties that are described in terms of probabilities. For example, checking a password with the wrong password returns false, but there is a small probability that a failure occurs where there's a hash collision. So this property only holds with a high probability. There are also certain properties that might be even hard to state. For example, that the password storage appears random to an outside observer. The second challenge with verifying real-world security properties, real-world security-related programs, is that the programs actually use quite a lot of complicated language features. Right off the bat, we can see the use of dynamically allocated mutable states for the mutable map. I can rewrite this function. If I don't want to expose the map to the user, I can try and encapsulate it and hide it within two higher order functions. And in this case, I will need to be able to support and reason about higher order functions. Maybe the language does not allow us to sample from a specific range of numbers, and the only primitive we have is that we can only generate a random 8-bit number. And for us to restrict the domain of the number generated, we need to implement it using a rejection sampler. In this case, we need to be able to reason about unbounded looping. Maybe the clients of this server is scattered all across the world and they might send requests at the same time, so we might need to be able to reason about concurrency on the client side, where requests are sent to the server at the same time. But there's also might be concurrency in the implementation. For example, in Linux systems, the way we generate numbers is that we read from a certain file, and there's a concurrent kernel thread that repeatedly writes random entropy bits into this shared file for different applications. So stepping back, in order to verify real-world security programs, we need to overcome these two challenges where we have to reason about probabilistic properties and also reason about programs that use a wide range of language features. Let us see how we can attack these two issues independently first. When I think about the first issue about reasoning about probabilistic properties, there's quite a lot of different prior work on verifying these probabilistic programs. There's the weakest pre-expectation calculi for reasoning about error bounds and expectations, a lot of different coupling-based logics for reasoning about relational properties. There are certain logics like Lilac and Bluebell which realize separation conjunction as probabilistic independence, and many, many more. However, these techniques often suffer the second problem, where the language they consider have certain trade-offs. For example, we might not be able to reason about shared state or concurrency with these techniques. To tackle the second problem, we can actually use IRIS, which is a higher order concurrent separation logic framework that is formalized in the proof assistant Rocq. And in recent years, there's actually quite a lot of work and success in using IRIS to verify programs with these challenging features that I've just shown you, like higher order functions or local state. The problem is that there isn't that much work in actually using IRIS to prove probabilistic properties. And hence, in my PhD, I try to combine the best of both worlds, where I develop probabilistic extensions of IRIS to reason about highly expressive probabilistic languages. And in this talk, I want to showcase a couple of logics that my collaborators and I are able to develop and reason about these complex programs. My PhD is roughly split into two stages. In the first stage, I develop IRIS logics specifically for reasoning about sequential probabilistic programs. And currently, in my second stage, I am extending the logics I developed before to reason about concurrency as well. To motivate these logics, I want to present a slightly simple example where we use the hash function again. Here, we are given two different inputs, and we hash these two inputs, n and m, with some deterministic hash function, where we produce x and y. And in security, as I mentioned before, as I hinted before, it is often useful to model the hash function as a collision-free random oracle. And by collision-free, I mean that different inputs are mapped to different outputs. And so we might want to prove a specification as so, where if m and n are different initially, the two values produced, x and y, will also be different. However, this is not always the case, because there is a small probability that a collision might occur. And we might want to reason about this precise error bound where an error might occur. To do so, my colleagues and I developed ARIS, which is a higher order separation logic for reasoning about error bounds of higher order probabilistic programs. The key idea of ARIS is that we internalize probabilistic error as a separation logic resource, which we call error credit. Error credit is written with this assertion, which we can read it as up to epsilon, and this epsilon is a real number that ranges from 0 to 1. Intuitively, if you own epsilon error credit, you are trying to prove the goal with at most epsilon probability of an error occurring. And you can see this more intuitively from the adequacy theorem, where if you can prove the Hoare triple on the left, assuming epsilon error credit to start with, then in reality, when you run the program, the probability that you get a value not in the post condition, hence an error result, is upper bounded by epsilon. And in the logic of errors, there are various rules, various flexible rules that allows you to spend error credits to avoid undesirable error results. For example, if with this rand n operation that samples uniformly from 0 and n inclusively, I can provide a list of numbers which I consider to be bad, and I provide an error credit proportional to the length of this bad list. And I can ensure that I will not be able, that the result of this rand n primitive will not be in the list. To show that this approach of error credit is very flexible, we proved a lot of examples, including this one where we actually provided a specification for the collision-free hash function I just provided, where you have to provide an error credit that is proportional to the number of times you have used the hash. With this specification, we derived an even more interesting specification where now the error credit is not proportional to the size of the hash, but constant. This can be done where we amortize the error credits across a fixed number of insertions. And this is easier to use from a client perspective because I don't have to know how many times I have used the hash function before when supplying the right amount of error credit. And it's also important to state that we're able to derive this specification just from the specification of the non-amortized version. And with this specification, to show that this is expressive and useful, we use it to implement various data structures like a Merkle tree and an unreliable data storage system. And we can show very nice error bounds of the probability of getting a right results when using these data structures. Error bounds are not the only property we want to reason about probabilistic programs. Sometimes these properties are described relationally. Take these two programs as an example. On the left, you have a pseudo-random function where each time you call it, it generates a random number. On the right is a pseudo-random permutation where we create a reference that points to an empty list, and every time we call it, we generate a number that is not in the list and append that, concatenate and add that into the reference. So in other words, the program on the right will always generate unique random numbers. And for the first few times you use these two functions, they appear to be somewhat similar. Well, not completely identical, but approximately similar up to some error, epsilon. And my colleagues and I developed a proxys which reintroduces the idea of error credits from errors from the unary setting to the relational setting that allows us to reason about this particular approximate refinement where we can compare two approximately similar programs. And this approach, we're able to reason about quite a lot of interesting security-related examples, such as the PRP-PRF switching lemma and the security of an encryption scheme. We also implemented a binary logical refinement relation within the logic of a proxys that allows us to prove contextual refinement, and we use it to prove the correctness of a B+tree sampling scheme that uses a complicated rejection sampling argument. Now, errors in a proxys are logics for sequential probabilistic programs, and currently I am extending these to reason about concurrency as well. And currently colleagues and I are able to develop logics of canaris and foxtrot, which are the concurrent counterparts of errors in a proxys respectively. One must emphasize that this extension is highly non-trivial. Reasoning about concurrency is difficult, reasoning about probability is also difficult, and reasoning about the combination of them is just pretty challenging. And here I want to highlight some issues that we encountered when developing these logics. For example, in canaris, in order to support modular specifying modular specifications of concurrent randomized modules, we realized that we have to capture something called randomized logical atomicity, and we will need new key ideas and features in order to capture this notion. In the relational case, it's even more complicated because certain rules that are sound in the sequential case suddenly are suddenly unsound and are not directly translatable to the concurrent case. In particular, in Aproxis, we use something called pre-sampling tapes to reason about complex distributions. And the rules that we write for pre-sampling tapes, some of them are actually unsound in Foxtrot, in particular the ones where you have to pre-sample on the right-hand side. And so to tackle these issues, we have to completely redesign the model of these logics and introduce new ideas that introduces new logical facilities and proof techniques such that we can recover as much expressiveness of the logic as possible. Some of the examples we're able to verify in Concurrency and Foxtrot includes a thread-safe hashes, which is similar to the hash specification I presented before, but now it is thread-safe in the sense that if two different or multiple threads use the same hash, the keys, the hashes will be consistent. So if two threads hash the same key, they will all produce the same output. We show that this specification is expressive by using it to implement a concurrent Bloom filter data structure. And we are able to show strict error bounds of getting a false positive with this data structure, which, to the best of our knowledge, is the first because of its interaction of concurrency, probability, and local state. In the relational case in Foxtrot, we're able to verify the correctness of a sampling function in the cryptographic library Sodium. In particular, we're able to show that its implementation is contextually equivalent to an idealized one. And it is important to emphasize that even though the implementation doesn't use concurrency, we're quantifying over all possible contexts that might even use concurrency. And so this gives us high degree of confidence that the sampling function is thread safe and can be safely used concurrently. Now that I've introduced you a couple of logics, let us take a step back and consider our original problem and ask, can we prove the properties of this password storage system? And the answer is that if we just want to prove the first property, where checking the password with the wrong password returns false with a high probability, we can express that as an error-bound result, and we can use errors to verify it. For the property where we want to reason about the password storage appearing random to an outside attacker or observer, this can be stated as a relational property, and we can use Aproxis to prove it. In the case where we even have concurrency on the client side, we can now use Concurrency or Foxtrot to prove the same properties. However, if we have concurrency in the implementation for this particular case, it turns out that it's not possible to verify certain security results using the logics I just presented. And the reason for this is that the concurrency model of Concurrency and Foxtrot are a bit too powerful in the sense that the schedulers we use to decide which thread to step has too much information about the whole program configuration. So an adversary can see the numbers generated into the file and decide which application would use certain bits. Now, this is not very realistic because in the real world, adversaries might not have complete information of everything you have in your software. For example, an adversary might not be able to see your secret keys. And hence, if we want to prove some interesting security results, we need to be able to reason about more schedulers with restricted power. And one future work in progress is that I want to develop logics and inspired by Concurrency or Foxtrot, where we internalize the idea of restricted schedulers and prove more interesting error bounds when we're quantifying over more realistic schedulers. In conclusion, verifying real-world security programs are challenging, and that is because we often have to reason or prove very complicated probabilistic properties, And these programs actually use quite a lot of complicated language features. And in this talk, I showed you a couple of logics where I'm able to take one step closer to achieving this dream where we can verify interesting properties of these programs. And in the future, I want to continue refining and improving the concurrency model of Canaris and Foxtrot that better reflects real-world adversaries and apply these logics to verify actual implementations of cryptographic libraries and protocols. Thank you.